This is CPE 233, lecture 18. And what we're getting into today is real-time programming, namely dealing with interrupts. So this is the introductory lecture on interrupts. So here we go. So my approach on interrupts is to introduce the concepts at a high level, and then later we're going to get into more in-depth stuff. But I'm going to give you some of the details. It's going to go by really fast. There's not that many details, but they are kind of confusing the first time you see them. So we're going to introduce them now, then we'll go over them in later lectures. The thing to note here is that interrupts are nothing more than a special subroutine, and this subroutine is special because it's initiated by the hardware. So this is as opposed to normal subroutines, which are initiated by a call instruction under program control. So this is a massively important topic. It's used, kind of forms the basis of real-time systems and just embedded systems in general. This can be massively complicated, but we're going to take a very simple approach to this. So this is going to be what you need to know for experiment 7. So this is the top level RISC-V microcontroller. And if you look at it here, let's see if we got a mouse going. There's a mouse going. Pretty much all these signals here are associated with I/O. So the only ones that are not early I/O are the clock and the reset signal. So this device, this microcontroller, is designed to do a lot of I/O, like input and output, which means it's gonna help you interact with your computer. So that's essentially the basis of embedded systems. So in talking about I/O, input output in computer systems, it's really, if you think about a computer, it's a piece of hardware that interacts with the outside world. So the way it interacts is by inputting data, maybe crunching it around, and then outputting it. So I/O is super important to any type of computer. So there's a couple types of I/O out there. We have been using up to now programmed I/O, and there's a couple different types of that. We were using memory mapped I/O in particular. There's also DMA, which is direct memory access, that you'll run into somewhere, not a part of this class though. And also we were going to deal with what we're moving into today is interrupt-driven I/O. And so essentially the way you look at this is that these programmed I/O is under program control. The DMA is initiated by external hardware, but then slightly controlled by the microcontroller. And then interrupt-driven I/O is initiated by external hardware, and that's going to be an important point. So if you think about it, what does a computer do? Well, it does whatever you tell it to. And typically in embedded systems, that computer is just sitting there waiting for you to do something, such as your phone. It's waiting for you, I don't know, to dial a number or surf the web or something like that. It reacts to your requests. So generally speaking, it's embedded systems like this. Embedded systems have a couple qualities. One is you want them to be responsive, such that when you tell them to do something, they do it. Okay, so we don't want delays in the response, or otherwise you think it's a sucky system. Also, we want to design our systems to have like an appropriate amount of computing for the job at hand. Look, we don't want to use a supercomputer to blink an LED. It would work great, but it would eat up a lot of power and just to be total overkill. Now, the third thing here is we want to keep the throughput of our system high, and the throughput is kind of the meaningful work done by our system, and we're going to modify that definition in the next slide. So like I said here, it's really hard to make generalizations, but the general idea of any computer system is keep the throughput high. And you know, that's easy to say, but it's not really always super practical. And so what you want to do is always have your processor doing meaningful things, and more importantly here, you don't want your processor stuck doing something stupid if you have something more important to do. So specifically, if you're stuck doing something stupid, your throughput's going to be low, your response time is going to be bad, et cetera, et cetera. So we're going to try to avoid that at all costs. So, when you're designing a computer system, like with a microcontroller, you have a choice. You can do all the work with the microcontroller under program control, or you can include some external hardware that does the work for you, and the microcontroller communicates with that external hardware. And one of the ways it communicates is via interrupts, and you'll see that come up next. So the idea here, once again, have the microcontroller do all your work for you under program control, or we can offload some of that extra work to an external hardware and have the microcontroller talk to it. So this is a huge design issue here as far as embedded systems go. The RISC-V order is very simple, so we don't really have to deal with a lot of that complexity. This is kind of an introduction to interrupts. They all do it the same way, except they have more interrupts. And once you have more interrupts, it gets a little bit complicated. But once again, we don't go there. Interrupts are considered some type of a type of I/O, which is kind of strange here. The idea here is we want to use interrupts to avoid polling and essentially boost our response time, and in addition to upping our throughput, and you'll see that come up next. Typically, when we're talking about I/O, we have two ways to do it. We can poll, or we can use interrupts. And so this is a piece of polling code here, and what it's doing is inputting the button value, masking it, and if that particular button is not set, it jumps back to inputting the value again. So this is fine, it works good. And then once we find that button press, we do something meaningful here. And the idea here is that if the microcontroller is in this loop here, it's going to be stuck in that loop. It's not going to be doing anything else. And we can't really break out of it until someone presses a button, which is potentially bad. So we don't want that. So interrupts, two primary uses. You increase the system throughput and increase the response time. So the idea here is of an interrupt is, like the name says, your processor is doing something normal, and then it stops what it's doing and goes and does something else. Now this is essentially the normal processing is interrupted to go do something else, and that's really where the interrupt comes from. And so what we're going to describe here is the RISC-V interrupt architecture. It's not super complicated, but there's a little bit to it. The more you study this, you will think, yeah, that's not too bad. It's really simple. It just does some simple operations, but you got to know those operations because you got to implement those instructions, we'll say, and implement that mechanism in hardware. So this is our programmer's model, and we've costed out this before, but what we had in there was a notion of there's like these three registers there. So these are three 32-bit registers. They're inside this CSR module, which is control and status register, and it's these three registers that are used to support interrupts. So inside the CSR, there's three 32-bit registers, and we indicate that inside the programmer's model. And as it implies there, we have the ability to write data to these registers. You'll see that come up next too. Subroutines are very close to interrupts. The idea of a subroutine is I execute a call under firmware control. What I need to do is I go somewhere and do something, but I need to first remember where to come back to. So I'm going to put the address of the next instruction after the call in the return address, or X1. And then I'm going to load the program counter with the address of the subroutine. And so the next instruction that's executed after the call is going to be the first instruction inside the subroutine. Okay, so I'm going to process a subroutine, execute a return. The return is going to load the return address back in the PC, and once again it works nicely. So so with interrupts, it's the same thing. I get an interrupt. What I'm going to do is do some operation here, which is essentially saving the return address, knowing where to come back to. So this is going to be the instruction after the instruction that was executed when I got the interrupt. I'm also going to load the program counter with the address of that special subroutine, which we call the interrupt service routine. And then I'm going to go process the interrupt service routine, and then I'm going to return. This is a special return instruction. What this does is it loads the address that I previously saved up here into the program counter. And so essentially it effectively returns from the interrupt, and life is good. So we're going to do a quick problem here. It's overly simple, but it has everything involved in interrupt architecture. I suggest you study this over and over again until it becomes second nature, because we're going to use this a lot, and a lot of this is going to show up on exams. And it's not that complicated. It's really not that complicated. If you know it, you're going to be bulletproof on future exams and stuff. So what we have here is, this is the RISC-V auto microcontroller. Here's the interrupt input. We're going to assume that some external device is connected to that, and we're going to do our problem here. And so essentially what it's going to do, this problem is going to toggle one of the LEDs. It happens to be the rightmost LED, and you'll see that come up next, and we'll go through this program. And here's the entire architecture. Notice that what's important here is I've tossed in this AND gate, so I have control over whether this interrupt signal actually makes it to the state machine. And the notion here is I have this signal here coming out of the CSR control and status register unit that either is a 1 or a 0, so it actually turns this gate on and off, which I like to say, or it passes this through, or it makes this 0. So this is essentially a switch here controlled by one bit in one of these registers in the CSR, and you'll see that come up next. So interrupt-driven programs a little bit different. Typically they have a init code, but initialization code, but now you actually have to initialize the interrupts too. You also have the main code, which is called the background task or the main task, and this is the code that's going to be interrupted by the interrupt. And so here's the interrupt code here, and what we have here is an interrupt service routine, and we're going to call that the foreground task. So what's going to happen is the microcontroller is going to be executing instructions, and suddenly gets an interrupt. It's going to go to the interrupt service routine, which is a different set of instructions, and it's going to execute those instructions. And when it's done, it's going to come back to where it was before it got the interrupt. This is our new state diagram for our the control unit FSM, and it now has this interrupt state in it. And so what you want to take away from this diagram here is a couple of things. So if the instruction is not a load instruction and I don't have an interrupt, I go back and just execute the next instruction. If the if that instruction, if at the end of executing that instruction and it's not a load instruction, there is an interrupt signal, I go into the interrupt state. Inside that interrupt state, I do a couple things. It's just one state, and then I go back and fetch the next instruction. So this is essentially the same thing for the load instruction. It just has an extra state there because we have the write back state associated with the load instructions. So you have the ability to turn the interrupts on and off, and it's essentially by writing to a certain bit, and it's a bit in one of the registers in the CSR unit. Essentially when that bit's a 1, it acts on interrupts when it gets them. If that bit's a 0, the microcontroller does not act on interrupts, and it has to do with, let's get this right, has to do with this AND gate here. And so we'll kind of delete all this. This signal right here is my control signal coming out of the CSR unit. It has the ability to let the interrupt signal pass to the state machine or not. So the processing here, this is, like, I know it's a quick introduction, but what I'm going to do here, then this is it seems like there's a lot to it, but I encourage you to spend time looking at this thing. So that what happens when you get an interrupt and the microcontroller acts on it? First thing, as you saw from the state diagram, it completes the execution of the instruction that it's currently executing. At that point, it goes into an interrupt cycle, and 4 things happen. One is the interrupt enable bit is cleared, so you don't get any more interrupts. Before that bit is cleared, it's actually saved in another bit. And what else do we have here? It's I'm going to load the address of the instruction that would have been implemented into another CSR register, which is the MEPC register, and then I'm going to take the value in the MTVEC register and load it into the program counter. So what you'll see later is I have to put the address of the interrupt service routine into the MTVEC record as part in MTVEC register as part of the initialization code for the interrupt. So after all that, it's just 4 things. I'm going to execute my interrupt service routine. It's just a bunch of code, and then I'm going to leave. I'm going to issue a MRET instruction, which stands for machine return. And what that's going to do is going to take my previously stored address, and this is the address of the next instruction that would have been implemented if I hadn't gotten interrupt. It's going to put that back into the PC, and then what it's going to do is going to take this bit right here, which was copied automatically from MIE, and put it back into MIE. And then after all that, normal execution is going to resume. So this is my code here, okay? And this is a very simple program, and I'm going to go through the highlights of this, and we'll go through this again later too. And so this is the blinking the LED program. Okay, so one of the first things I need to do as part of the interrupt initialization is write the address of the interrupt service routine into MTVEC. So there it is. What I'm going to do is put that address into X6, and I'm going to write X6 to this instruction. And I'm going to use this new instruction here, which is control and status register read write. It's going to simultaneously write X6 to MTVEC and write the value in MTVEC to X0, which effectively for our code does nothing. This is just simply setup code here. I do have a register, which is X8, that I'm going to use as a flag register. Okay, so it's just a flag. It's just a Boolean. Okay, and that's another thing you'll see it in the code here. And then what I'm going to do here is unmask the interrupts. Okay, so that there's a certain bit in the M status register that I have to turn on. It happens to be the 3rd bit from the right, which I'm going to indicate by X8. And so if this bit in if that 3rd bit in X8 is set, well, I'm going to set it in X10. What it's going to do is set the 3rd bit in the M status register because I indicated that in register X10. So X8, remember 8 is this. This is bit 3. This is the MIE bit as defined by the RISC-V spec. So next thing here is that it ends up in this loop here. This is essentially a polling loop. Yes, I know, but just keep it simple here. And what it's doing is checking X8. Well, I made X8 0, and there's no code here that changes X8. So how do I ever break out of this loop here? Well, I get an interrupt. So inside the interrupt, first thing I do is load a non-zero value into X8. The next thing I do is I clear the MPIE bit inside the M status register. And once I clear that bit, when I execute the M return, what's going to happen is it's going to copy the MPIE bit back to the MIE bit. Now MIE bit is going to be once again, it's going to be the interrupt enable. I cleared the bit using this clear instruction, right? So it's cleared, and now the interrupts are going to be disabled when I return from the interrupt service routine, and it's going to return up to here. One of these instructions, the X8 got set to 1. This little tight loop here is going to fail, and it's going to go down to these instructions right here. So this is the blinking the LED code, but the important part here is once I get all that done, I need to turn the interrupts back on, and you can see I'm going to use this instruction here, CSRS. That's going to set the particular bit in X10. You can see that this code is the same as this code up here. And that's the world's simplest program. It's described in gory detail in the book as well. I don't want to keep this video, make it too long, so we're gonna move on. So yes, this is the big architecture here. Once again, this is an important gate here where this is intimately involved in enabling the bits and enabling the interrupts. Here is the MIE bit coming out of the M status register, which is used to control this gate, which is used to pass the interrupt signal to the FSM or not. And that's all, folks.